Um, I'm happy to share our paper, Complex Evolution Pattern Learning for Temporal Knowledge Graph Learning. This is the only work while we're doing internship at Baidu. Um, okay, I have code these days, and I'm sorry for that. Uh, uh, but actually, this is a short paper, and it may not take our to it may not take us 1 hour. Okay, and we all know that knowledge graph have facilitated many real-world applications, which use subject-entity relations and object entity to describe the facts in the real world. However, traditional knowledge graph can only store the static facts. Temporal knowledge graphs considers the time validations of facts by describe a fact using the wrappers, which is the subject entity, relation, object entity, and the timestamp. TKGs are used to describe the events and association among events. Here are two examples of the TKGs. um, there are two there are two settings of temporal learning task. The first one is the interpolation setting. It aims to inform missing facts in history to complete the TKG, which is also called the TKG completion task. It will given some facts from timestamp 0 to t, and it aims to complete the missing facts from timestamp 0 to t. And the second setting is extrapolation setting, which will give the historical facts from 0 to t and predict facts in the future, such as predict facts at timestamp t plus 1. And my works are focused on the second setting. It can be seen the exploration TKG learning task under the exploration setting can benefit many real applications such as disaster relief, financial analysis, and so on. Okay, let us talk about the related work. There are some works. Let me first talk about the models for interpolation setting. The first work is T trans E. T trans E. This work it seems it gives it learns presentations for each timestamp, and it replaces the relation embedding by the it replaces the relation embedding in trans E by 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 multiple the relation embedding with the matrix. And the second work is TA trans E. It seems the timestamp as a sequence of numbers. For example, it considers the year 1986 as a sequence of numbers 1986, and use a sequential model such as RNN to model the number sequence as well as the relations to get the time a while relation embeddings, and use this embeddings to replace the relation embeddings in trans E models. And HITE, this model associates each timestamp timestamp with a hyperplane, and it project the relation embedding and the entity embedding to each hyperplane to get the embeddings under of different times to get the time a while entity embeddings and relation embeddings. Okay, but these models under this setting cannot predict facts in the future. And in recent years, there are some works for the extrapolation setting. There are two earlier work. These two work, the main idea of them is to extract some facts from history and model them and to predict the future. INET first it extracts the subgraph related to the subject entity in the query, and then it use a subgraph aggregator to get the embeddings of subgraphs at a different timestamp, and then it uses GRU to model the subgraph sequence. Based on the presentation output by the GRU, it gets the probability of all entities in the future timestamp. And CYGNet uses a sequential copy network to model the repetitive facts. There are three limitations of this work. First, they negate the structural dependencies within KGs. They only models subgraphs that extracted in a hierarchical manner. Two, there are no efficiency because they encode the history for each query individually. And three, they ignore the function of some static properties of entities. Thus, in SIGA 2021, we propose IGCN model. Let me take some time to introduce this work because the topic of this report is directly related to this work. IGCN views the TKG as a sequence of KGs, and it designs a evolutional unit to model the graph at each timestamp. By reusing the evolutional unit, it gets the final evolutional presentations of relations and entities. Specifically, in the evolutional unit, it uses a relation while GCN to model the structural dependencies among the concurrent facts, and it uses two gate recurrent components to model the sequential patterns of temporally adjacent facts, and it uses a static graph constraint component to model the static properties of entities. Okay, the first there are two kinds of information among the concurrent facts. That means association among the entities through facts and association among relations, so the shared entities. Thus, we use the GCL and relational wire GCN component to model the structures among the concurrent facts. It is actually the message passing framework that yes, and we use the two gate current component to model the historical sequence auto-regressively. For at each timestamp, the relation embedding are calculated by GRU with the embeddings of the relation embeddings at the previous timestamp and the embedding calculated by the entities embeddings by the pooling operation over the entity embeddings at the current timestamps. And then finally, they use the GRU to get the relation embedding at the current timestamp. And for the evolutional presentations of entities, it uses the use the tangent component to avoid the oversmoothing problem in Zixuan. Know that because that the historical sequence we modeled may become longer when the historical facts we modeled become longer. Thus, the Zixuan layer may be deeper, and the oversmoothing problem may appear. Thus, we use the tangent component to avoid this. Specifically, the finally entity embeddings are calculated are from two parts. The first is the output of the Zixuan component at current timestamp, and another is from the previous entity embeddings at the previous timestamp, and we calculate the gate value according to the previous according to the evolutional presentations of entities at the previous timestamp. And the static graph constraint component is to model the static properties of entities. First, we construct a static graph according to the name of entities in the TKG. For example, for the entity government USA, we add two H's to the entities. And that means government USA is a government, and the government USA is the country of the government USA is USA. This we extract some static information and construct a static graph, and then we use the RGSM to get the static embedding of all entities, and use this embedding to constrain the evolutional embeddings of entities at a different timestamp, and get the constraint loss. After we get the evolutional presentations of entities and the relations, we use the convol-trans-E decoder to calculate the probability of entities and relations. Convol-trans-E model, we first look up the evolutional presentations of entities and relations, and get the embedding of the entities, the subject entity and the relations, and concat them to a 2D matrix. Then we use the 2D kernel to conduct convolutional operation in the embedding and get the feature maps. We can concat this feature maps to a vector and feed it into a fully connected layer to get the get a final embedding with a dimension of one multiple d. D is the dimension of the anti-presentations, and finally we multiply the embedding with the evolutional presentations of all entities to get the logits of all entities. And then we calculate the cross-entropy loss according to the logits and the label. Okay. Okay, let me talk about the CEM model. We think one key of TK learning to mine and understand evolutional patterns from KG sequence. What is the evolution patterns? And we think we think there are some temporally adjacent effects that with the informative sequential patterns, and the goal to learn evolutional presentations is to mine these patterns from the historical facts. But the evolutional patterns are complex in two aspects. First is nonce diversity, which means the nonces of evolution patterns are diverse. For example, we can then a sequential pattern of non 3 from these three facts, and we also can learn a shorter evolutional patterns from these two facts. But these facts are all useful for our prediction. Previous work such as IGCN takes the historical sequence with a fixed nonce as input, and we think it's hard for them to learn the nonce diverse to learn these nonce diversities. And another aspect is time variability. That means evolutional patterns change over time. For example, COVID-19 inject A 2019 and COVID-19 inject A 2022. These two things may lead to different results due to the widening usage of the COVID-19 vaccine. But previous work always train their model in the previous time in the training data, and test their model in the test data at a future timestamp. Results update their models after training. Thus, we propose the complex evolutionary network. It contains a KG sequence encoder and a non-survival score function. A KG sequence encoder is similar to our previous work IGCN, but the differences between them is that CN takes K historical sequence from nonce 1 to K as the input of the encoder, and get K evolutional presentations. Yes. We can skip this component because it's very similar to IGCN. We remove the static graph constraint and replace the structure dependency structure dependency component with the IGCN component. After we get K evolutional presentations, we design a relational Y score functions. Score function. First, we calculate we look up the we look up the evolutional permutations and get the query embeddings by concat the embedding of subject entities and relations. Note that there are k embeddings for a query, and each embedding are corresponding to a historical sequence of a fixed norms. And then we calculate the feature map of k query presentations. Note that we use k kernels, k channels, and each channels correspond to a embedding in the left, and it's different. It's a little different from common transit because we have k channels and each channels have c kernels. Yes. Thus we get the C feature maps. After we feed C feature maps to a shared one layer FCN and get the C embeddings with a size of 1 multiple D. And then we multiply this C embedding with the evolutional presentations of all entities and get C logits. And finally, the score are calculated by sum up these logits. Yes. There are another intuition is that we think that a longer history sequence contains more complex evolutional patterns and is more harder to learn for the model. Thus, we take the curriculum learning strategy to train our model with the from easy to hard. That means we first take the historical sequence with nonce one as the input of our model and train the model in the training data. And then we increase the historical norms and retrain the model in the training data to get the next model. We will stop increase the norms of historical sequence when the MRR matrix decrease in the validation set or the norms of historical sequence is equals to the maximal historical norms of it, maximal norms of historical sequence K. And for the time variability, we adopt a simple and direct strategy, which means we conduct online learning for our model. That means we continuously fine-tune our model along the timestamp. For example, to predict facts at timestamp t+1, we will fine-tune the model tk by predict the facts at timestamp t, and then we use the updated model to predict facts at timestamp t+1. And one problem in online learning is that model will forget some knowledge at the past at a previous timestamp. Why they learn new knowledge at future timestamp. Thus, we we adopt a temporal aggregation unit to avoid this problem. We use the L2 regularization constraint between the parameters of model Tk and model T plus 1k to avoid the drastic change of parameters of models. We conduct experiments on 3 datasets. They are ICWS 14, 18, and Wiki. Results shows that CN performs better at almost all the datasets, which proves the effectiveness of modeling the nonce diversity of evolutionary patterns. And we also conduct experiments under the online setting. Note that model trend under the online setting cannot be compared with the models under offline setting directly, because model can see some facts at the timestamp at the test timestamp. Thus, we report results in another table, and we compare CEN with CEN without temporal regularization unit. It can be seen that on the dataset ICWS 14 and 18, temporal regularization unit can help the model to avoid the forgetting problem, and the CN gets a better performance. But on the dataset wiki, a dataset that has a time guarantee of 1 year, the CN without temporal regularization unit gets better results. That is because that in this data set, the time guarantee is much larger than ICWS datasets. The change between timestamp are drastic, but the temporal regulation unit limits the model to adapt to the new facts, and thus make the performance decrease. We also conduct ablation studies. We remove the curriculum learning strategy and nonce a while and replace the nonce a while decoder with original convol trans-E. The underperformers also prove the effectiveness of the proposed component. Okay, we release the code and dataset to the under websites, including IGSN and CN. Okay, that's all. Thanks. Any questions?
Thank you very much.
Thank you very much.
Write a lot of notes, but I can't see that. So I think my English is poor.
Oh, that was very good. Thank you.
If there are some confusing, please ask some questions about confusing.
Thank you. I think it was very understandable. I have a question on the implementation. So you have the slide where you have the figure. If you go back a few slides. This one, yes. So here you concatenate the embedding of the node with the relation embedding. Is the relation embedding, is this also dynamic or is it a static relation embedding?
This is dynamic imbalance. Yes.
So also the relation embedding evolves over time.
Relation imbalance are not evolving over time in this model.
Okay.
Yeah.
Thank you.
It's also a little difference between this work and Zixuan, because we also make the relation embedding changes over time, but it cannot improve, but it improves a little. Yes. So we remove this unit.
So you did a study from the RGCN dynamic relation embedding and you found it improves only little. And this is why here you have the relation. Okay, thank you. That's interesting. And that's another question that I have here. Or sorry for interrupting.
Also this slide, this page.
Yes. So you also said that from RGCN, you do not take the static constraint. Is there a reason? Because I think it helped in RGCN, right?
You mean you want to know the reason that we do not use the static graph constraint in this work?
Yes.
I think this is not the contribution of this work, and the static graph constraint is one way to introduce some external knowledge, such as some static knowledge, but integrating static knowledge is not the main contribution of this work. So do not add this component. Yes.
Okay, thanks for explaining.
One interesting thing is that we conduct the experiments. When we conduct the experiment, we found that you can see some it looks like the ensemble of K historical sequence. It looks like that the CN is the ensemble of K models, each of which models historical sequence of different nodes. Yeah. And we want to make the model share some parameters in the decoder. Yes. So the note that the KG sequence encoder is shared the evolutional unit when modeling different historical sequence. Yes, the parameters of the encoder is these are shared. The parameter of this are shared, and in the right part, we also want to share the parameters between the different kernels and the CN, the FCN layer. But we found that if we shared parameters in the non-survival CNN, the performance decrease drastically. So we use the non-survival CNN and use the different kernels for the different evolutionary presentations. But we also found that the shared CFCN cannot do not influence the performance. Yes. Any other questions?
Yeah, I have one question about the temporal knowledge graph creation. So how difficult, since a lot of the knowledge KG dataset available, they are not temporal in nature. So how hard it is to create the temporal sequence of the knowledge graph?
Can you speak a little slow?
Yes, so my question is, we have the KG available, lot of KGs available where we test our model. So how difficult or what is the process of creating temporal KG? So is there some tools available to create temporal KG, or have you created manually?
Can anyone translate the question for me? I think
I
there
have
are
written
some
it in the
accent.
chat. Maybe it will be helpful.
I think there are some accent in your questions. I can understand.
The question is, did you create the temporal knowledge graph dataset, and was it difficult to create the dataset?
Yeah. In this two work, we do not create a dataset. This datasets are created by the previous work, but we are doing some works that creating new datasets for this area, because we know that TKG nowadays TKGs are noisy because the TKG are constructed by the automatic algorithms. For example, ICWS dataset and GData dataset. It's noisy, and the way to describe dynamic facts or say events by a Corti wrapper maybe not enough. We all know that events have more than two arguments, more than subject entities and the object entities. How to describe the facts more comprehensively? We are doing some new works on it and we propose some new data sets. Yeah.
Yeah, great to know. Thanks for answer.
Do you already have a publication on the new data sets?
No, the paper is under review, and I also revising this paper. I think it's a good work, and maybe I will make it public as soon as possible.
Yes, if it's finished and public, please let me or let us know. I think many people are interested in that. Also in the chat, Roxana says she's also interested.
Thank you. Is there anyone has questions?
I had just one question. You mentioned that you have removed the static graph representation in your later work.
Yeah.
Can you explain a bit more about the intuition on that?
Oh, okay. I think in this work, the most contribution and the motivation of this work is to solve these two questions, which means the noise diversity and time variability of evolutional patterns, but not to introduce some static information into the evolutional presentations. So we focus on solving these two challenges and do not using the static graph component. I think if you add the static graph constraint in the KG sequence encoder, the performance of CN will increase. Increase. Yeah. But it is not the main contribution of the. It's not a main problem that we considered in this work, so we do not add this component.
I see. And also, you have specified the length equal to k. So how do you compute the k value here?
Yeah. Yeah. Maybe I do not tell these details clearly in. It is decided in the curriculum. It is decided in the curriculum learning procedure. That means when we train our model, which from the historical sequence of nonce 1 to nonce k, we stop increase the nonce of historical sequence when the performance of our model decrease in the validation set. That means k is adaptively decided in the curriculum learning procedure. First, we let k equals to 1 and 2 and 3, and if the MR metric decrease on the validation set, or k equals to the maximal nonce of historical sequence. Maybe you set the maximal nonce to 10, and it will stop when k equals to 10.
I see. Yeah, that makes sense. Thank you.
Yeah. Yes. I think this is another function of learning. And in one aspect, curriculum learning makes our model learn from easy patterns to hard patterns, and in another aspect, it adaptively decides the hyperparameters in our model. Yeah.
Yeah, that's very interesting. I don't know whether any other people have any question, but if you have any question, please raise them. So if there's no more question, let us thanks again the speaker for the great presentation, and we will see you next week.